Look at you.
I know.
I mean, it's almost like you're a grown woman.
Personal growth. Personal growth. We accept what we can. Okay, so Unit 3, we did not look at this unit as a unit. We chunked up various portions of this. So this is going to seem like a bit of a mishmash because this is intermolecular forces, but also solids, liquids, gases, and gas laws. So, yeah, let's begin. There are 4 videos here because all the topics are, like I said, kind of mishmashed together, so it was a little harder to go from one to another. So they've got 4 different videos here, and we're gonna start off with intermolecular forces. And intermolecular forces go right off of structure and polarity, which is where we ended last week. So you can't assign an intermolecular force if you don't know the structure and the polarity, with the exception of one. You can assign one of the intermolecular forces because everybody has it. Which
London
one?
Dispersion Forces.
There you go. London Dispersion Forces. Everybody gets those. But the other ones require some form of polarity. So that's all this. So let's go through the types. So these are the things that are between molecules. These are not bonds. We are specifically saying forces, not bonds, because they are in between the entire molecules themselves. So our bonds are the things that are going between the atoms, forces between molecules. Okay, so our 4 main types: the London dispersion forces, dipole, hydrogen bonding, which we hate the fact that they use the word bonding there because it's not a bond, it's a force, and ion-dipole. Okay, so we're going to go through them in that order. London dispersion forces. These are a result of your Coulombic attractions between temporary fluctuating dipoles. So this is what we refer to as an induced dipole. You remember it's with the little thing when we did the diagram with the sheep and they were wandering around, and if the sheep were all evenly in the field, there was no dipole, but if the sheep just kind of wandered into more one part of the field than the other, there was a temporary dipole. There's a packet with sheep in it. That's what we're talking about. Okay. So everybody has London dispersion forces. And when we are talking about large molecules, they tend to be the actual thing that is the strongest, because these are going to increase based on the surface area. All right, so the larger the thing is, you can have more zones of temporary dipoles, but also they are going to increase with the amount of the electron cloud, because it is the electrons that are actually shifting and becoming a temporary dipole. So if you have more electrons, there is more possibility for them. So, right, increase with the number of electrons, and also by having multiple bonds. So the answer here, while it is larger molecules have stronger London dispersion forces, it's not because of mass. That is what people tend to say. It is because of the number or the amount of electrons. And I think I stressed that pretty well when we were going over this. But London dispersion forces is kind of based around the number of electrons. More electrons equals stronger London dispersion forces.
Miss Baskin?
Yes.
But these forces, these are the weakest ones, right? So.
Well, you got to be careful. They can be weak, but they're in small molecules, they're weak. In large molecules, they're actually quite strong, because if you have like hundreds of electrons, that's actually ends up being quite strong. But this is the only force that non-polar molecules have.
Okay.
Yeah, non-polar molecules can only have LDF because they ain't polar, so they can't make a dipole. Okay. So there's your diagram of it. Okay, so next you get dipole forces, and dipole implies pole, implying polarity. So you have to have a polar molecule here. So this is when you get an attraction between a positive end of a polar molecule and a negative end of a different polar molecule. The most common of these is when you have just two polar molecules. That's what they normally ask. But you can have a polar molecule and a nonpolar molecule that forces it to be that way. Not as common. They normally only ask about dipole-dipole. So we'll just stick with that. Polar molecules. We're always talking about attraction because we've got a partial positive and the partial negative. And the more polar the molecule, the stronger the dipole interaction can be. So in general, these are stronger than London forces when we are comparing things of similar size. So that's what you got to be careful about when you want to say it's like it's the weakest force or the strongest force. You have to know what you are comparing it to. And so you can only make those comparisons when you are talking about molecules that are of similar size and shape.
Just asking.
Yes.
So for when increasing the dipole, that means like is that saying like the things that are in the molecule have
I think I know what you're saying. Let me.
Okay. Break it down for me, please.
So meaning like if I have, oops. That is a polar molecule.
Mm-hmm.
And you would get a partial negative here, right? Because that's more electronegative, and all of this over here would all have partial positives. But that is also a polar molecule. Because this would also be a partial negative, and these would also have partial positives. This one is more polar and would have stronger dipole forces.
Okay.
Because it's more polar. But I can make that distinction because these are similar size and shape.
Okay. That was my question.
Yeah.
And when it comes to like a specific electronegativity, I mean, we can always do it based on like fluorine and stuff, but will they give us like the numbers?
No, because all it's ever going to be is closer to fluorine. In fact, a lot of times one of the things, if they ask you to do a comparison like that, often one of the things does have fluorine and then the other thing does not have fluorine. It has something else, so to make it fairly obvious.
Okay.
Yeah. Okay. Okay. So like, just like what I drew, those partial positives, partial negatives, that's what you're actually getting in terms of those actual forces. Like I said, the induced dipole, we don't really talk about too much. So we're just going to stick with talking about straight between polar molecules. Did you go outside of the house to get a Dunkin' Donuts?
No, my dad did.
Now your dad's got corona. Come on.
No, he doesn't. It's okay.
Whatever. You got a snowman on the wall. What is that?
I'm in my dad's office right now. And that's my brother's artwork from like when he was like in preschool.
Okay. Hydrogen bonds. Hydrogen bonds were a special case of dipole, right? Hydrogen bonds are basically dipole interactions, but only of a very specific subset, and they're slightly stronger. So they're not bonds. They are forces, hydrogen forces, but they are our strongest type of force. And they are strongest because hydrogen is so itty bitty that it allows for a superpolar bond to be formed. Okay, so this happens when you have hydrogen bonded to nitrogen, oxygen, or fluorine, all right? Nitrogen, oxygen, and fluorine are both really electronegative, but also really small. And so you end up with a very, very polar bond. The nitrogen, oxygen, and fluorine are going to be extremely partially negative, and the hydrogen will be extremely partially positive. And therefore, it is such a great difference between the two ends of the bond that it allows for a very, very strong dipole bond to be formed with something else that has that exact same setup. So the trick here is you're looking for hydrogen with NO and F. That's the only way it's going to be a hydrogen bond. And so looking at this diagram here, what they've done in years past is ask you to either draw on a diagram where a hydrogen bond would form. And I know I asked you to do that on a quiz back in the fall, or they would present you with a diagram with various different options and say which one of these is the hydrogen bond. So the thing you can look at, like on this diagram, the hydrogen bond, it's not in the molecule. Again, it is between the molecules, but it is between a hydrogen and either an N, an O, or an F. It has to be between the N, the O, and the F, and the hydrogen. All right, so you can't make a mistake there. And then the number one, example of hydrogen bonds is water, right? Hydrogen bonding is what makes water so special.
Wait, Ms. Baskin, I'm confused.
Yes.
Slightly. So you said it's not a true bond because bonds happen between two different molecules. Like this is happening inside of a molecule?
No, bonds technically happen inside of a molecule between atoms. Forces happen between molecules. This is happening between molecules, so it should be called a hydrogen force. Stupid biologists called it a hydrogen bond because they don't know.
I'm sorry, can you say it again? If the bonds happen between this and then the forces happen between this?
Yes. So let's see. Let me switch to red. Okay. So that is a bond, right? It is between, it's a solid line between two atoms inside the same molecule. Whereas this, the dotted line, is a force. And it's a force because it's between two different molecules, right? The hydrogen and the oxygen in this force are from two different molecules. They're not from the same thing.
Ah.
Okay. So this should be hydrogen force. And we can blame biologists for calling it a bond because that's where it came from. But it is a force. It is between molecules. So the other thing to note here is that you can't have a hydrogen bond, say, with this hydrogen. Why not?
Because it's not connected to an oxygen, nitrogen, or fluorine of the other molecule.
Yes. So this hydrogen down here, or this one, any of these other hydrogens can't make hydrogen bonds because they're bonded to carbon. And you can only make a hydrogen bond if that hydrogen is bonded to the NO or the F.
And so is it, okay. I understand, so it's a force. So it's like interacting between where the blue line is, the dotted line. That's like the hydrogen bond.
Yes.
But, so does it, because I see in both these cases, like the O on the right side is also connected to another hydrogen. So is it just the hydrogen and oxygen in question, or is it because they're both also connected to other oxygen and hydrogen that make it a hydrogen bond?
The hydrogen has to be connected to an NO or an F,
Okay.
The oxygen does not necessarily, right? Like it can
Okay.
bond to another NO or an F in this other thing. But this hydrogen here would also make hydrogen bonds.
Okay.
Right? Because it's bonded to this oxygen.
Okay, got you.
Okay. Oops. Okay, so the last one is ion-dipole forces. And this is basically like instead of two polar molecules, you get a polar molecule and just a full-on straight-ass ion. So we have partial charges and full charges that interact here. So ions and polar molecules. This is what ends up happening when you dissolve salts and stuff in water. You have the ions from the salts and the water, which is really polar, so you get ion-dipole forces. These are stronger because now you're talking about, instead of partial charges, full charge and partial charge. So like I said, this is the classic example where you are basically dissolving salts in water. So you have the full charge of the individual cations and anions from the salt surrounding by the polar molecule, in this instance, water. So ions can have these attractions with polar molecules in a way that they can't with nonpolar molecules. So, and everybody's been getting the correct orientation of your water molecules on your ions, so that's good. You got to remember your oxygen is your little negative and your hydrogens are your positives. Okay, so let's do some practice problems. So again, we know that they're not going to have you draw anything. So it's more likely that you would have to look at a structure and decide what kinds of forces something may have. So here's a question. At room temperature, fluorine and chlorine are gases, bromine is a liquid, iodine is a solid. Explain this pattern.
Does it mean explain what bonds or what forces are happening in between these things?
Well, the forces are explaining the different states of matter. So part of what you have to do is decide who's got the strongest forces. And you can tell who's got the strongest forces because they've given you that information via the state of matter. So who's got the strongest forces?
Iodine.
Iodine. Because
it's like a solid, it's connected together.
Okay. So then why would iodine have stronger forces than bromine or chlorine or fluorine?
It has the most electrons.
It's got more polarizable electrons, right? It's got more electrons. So all four of these things are nonpolar, right? Because it's a thing bonded to itself. Like by definition, that is nonpolar. But because iodine has the greatest number of electrons, it's the most polarizable, so its LDFs will be the strongest. Mm-hmm. So this is a classic explanation for London dispersion forces, for LDFs, like how you would say that iodine has the strongest LDFs. So this kind of language is really good for explaining LDFs. That's one of the reasons why we left this one up there. Are you sneaking a scone? Okay. Okay. So which of these following, which I'm about to put up, are going to have the strongest ion-dipole forces, right? So this is full charge, partial charge. So between all of these, so the highlighted answer is aluminum. Why would that have the strongest ion-dipole forces?
It has the largest charge.
Largest charge, right? So remember, all of this stuff is still dictated by Coulomb's law. So amount of charge and distance is what we're dealing with. So whoever's got the highest amount of charge is going to have the highest amount of attraction, which is all the force is. Okay. Okay. So it says, which of the following will have the lowest equilibrium vapor pressure? Well, shit. So you got to think about what is vapor pressure and how on earth does that relate to intermolecular forces? So vapor pressure. Do you remember what vapor pressure is when we talked about gases? Vaguely.
Nope.
Nope.
I mean, vapor pressure. I mean,
I do not.
I remember
John tried to
it's like,
because we'll make him remember. He said vapor pressure.
I remember that when we were talking about equilibrium, right? I don't know if this has, because it said equilibrium, but I don't know if it has much to do with that. I remember that like when, like there was rules with gases, like if you increase gas on one side and stuff like that. Is that this?
Okay. So if I have a container and that container has a liquid, remember that some of those liquid particles are up here as vapor, right? Because vapor is what we call the gas state of something that is normally a liquid, right? Like above a glass of water is always some water vapor regardless of the temperature. But if I put a lid on this thing, now I've got a closed space, and that closed space and this vapor exerts pressure. Okay. So if I have more pressure, does that mean I have more vapor molecules or less vapor molecules?
More.
More vapor molecule.
More pressure equals more vapor molecules. Okay. So if I have more vapor molecules up there, what does that mean for the attraction between the molecules? Does it vary high
It's
or is it
little.
very low?
Very low.
Very low. More vapor molecules equals low attraction between those molecules. Because otherwise they wouldn't be a vapor. If they have strong attraction, they're going to stay a liquid. But if they have weak attraction, they're going to be like, yeah, I'm cool being a gas. That's fine. So then, looking back at the question.
Miss Baskin, can you
Yeah.
wait 1 second? Never mind. I wanted to draw it.
Oh, okay. No, that's easy.
Thank you.
Okay. Okay. So it says, which of the following will have the lowest vapor pressure? So is lowest vapor pressure, how does that relate to attraction then? Strong or weak?
Strong.
Strong. Strong
Oh.
because low vapor pressure means you hardly have any vapor. If you hardly have any vapor, that means you have really strong attraction because everything stayed as a liquid.
Okay.
Okay. So which of these basically wants to stay at a liquid? Nitrogen. First off, is that polar or non-polar?
Non-polar.
Non-polar, because it's two things
Anything
bonding
bonded
with
to
itself. Yep. So that's only got LDFs. CO2. You remember if that's polar or non-polar?
Is it polar?
No, this guy is not because he's symmetrical.
Yeah.
So the C double bonded to the O,
Mm-hmm.
double bonded to the O. So he's got symmetry. So therefore he is non-polar.
So Ms. Baskin,
Yes.
I know you said in the beginning that like structure and shape, that's kind of how you determine these forces and like the dipoles and all that type of stuff. So like thinking of a possible FRQ, would it be like a type of problem when they're like, what is, you said they aren't gonna have us draw, but like, what is the structure of this thing? Based on its structure, what forces would it have? And then ask us questions about like stuff like this, like different things that the forces could influence.
Yes. So I think we are much more likely to have a question that some random thing about vapor pressure that gets at that you can't answer without knowing the force. So, yeah. Okay, and then we have CH3Br and CH4. So CH4 is also nonpolar because of symmetry.
Ooh.
Right? So C with the H, the H, the H, and the H, that's all symmetrical. But this guy
It's polar.
is polar because he's got the Br. So he's got a very recognizable partial negative. I am damn proud I just did that with my figure. All right, so
Good job.
thanks. I mean, that's a hard symbol to draw to begin with. So that guy is polar. And since he's the one that's polar, he's going to have the lowest equilibrium vapor pressure because it's most likely to stay as the liquid because it's got the strongest attractions. And what kind of attractions does the CH3Br have?
Hydrogen? Okay.
No.
No hydrogen bonds. There's no N or F there.
Carl.
Carl, why'd you say it like that?
Is it just dipole?
Dipole, right?
Oh. So why is it dipole?
Because it's a polar molecule.
Okay.
So that's literally it.
Mhm.
So, I guess you couldn't ever really say anything is ion-dipole without comparing it to something else.
You literally have to have an ion present to have ion-dipole. So again, ion-dipole interactions, they typically only mention them when we are talking about dissolving a salt in a solvent of some sort. So like a salt can dissolve in water because there's ion-dipole interactions. Salts can dissolve in alcohol because the OH in the alcohol does also give you a slightly polar molecule and you can have some. But like you can't dissolve a salt in CH4 in methane because it's nonpolar. So there is no such thing as an ion-induced dipole. That is not a thing. Okay. Okay. So here's one where we're going to present you with the diagram. So in this diagram, what thing is the hydrogen bond?
The O and the H bonds?
The dash line.
The dash lines, right? It is the thing literally between the molecules. So it's not the solid line, it's always a dashed line. It's never, ever, ever going to be solid lines. We show bonds with solid lines, attractions with dots or dashes.
So that's a consistent thing.
Yes.
Like across. Okay, so that's like one of those easy questions, like 3 points.
Yeah.
So
because even on like prior tests where they ask you to like draw a hydrogen bond, they even in the scoring guides they specifically say that like your answer can't be a solid line, like you have to represent it as a dotted or a dashed line.
Okay, so Miss Askin, like when it comes to hydrogen bonds being like the strongest intermolecular force, right? Then why is water so easily turned into vapor? Like if it's supposed to be like super strong.
Oh, it's not. If you compare any other molecule of the same size or mass as water, it's more like you can't ever get them to be liquids.
Oh, okay.
Yeah, they all exist just as gases except for like super negative temperatures.
Okay, so it's like I guess so. Okay, I see what you mean. I see what you mean.
So like methane has almost the exact same mass as water, and methane's gas. Like to liquefy methane, it's like several negative 100 degrees.
Okay.
Yeah.
Okay.
Okay. So here's another one where they've given you some structures and they're going to ask you some questions. So without even looking at any of the questions, looking at these two things, are these polar or non-polar molecules?
Polar.
Non-polar.
Non-polar, because they're symmetrical.
They're very symmetrical.
They're very symmetrical, and there is nothing but carbon and hydrogen in here. Okay. So if both of these are non-polar, then I can already anticipate what kind of forces are at play.
LDF.
LDF. So who's going to have the stronger forces here? The thing on the left or the right?
The right.
On the left.
The right.
The left, because is it left?
The right has more electrons.
The right, because it's got more electrons. Right?
Okay.
If we are making comparisons about LDFs, the only thing we care about is the number of electrons. So then the question is, would you expect propane, the thing on the left, or octane, the thing on the right, to have the lowest boiling point? And think about what it means to have a low boiling point.
Propane.
So boiling point is when you go from what to what?
The boiling point is when you go from
Liquid to gas.
liquid to gas.
Liquid to
And
gas.
if you have a low boiling point, that means you have weaker forces. So the thing on the left
Yes.
would have a lower boiling point.
So that's always the thing about these types of questions, is you have to think about what specific, case that they're asking about. What does that mean for forces? So low boiling point means it's super easy to go from a liquid to a gas. If it's easy to go from a liquid to a gas, that means you have weak attractions. So propane is the one with the weak attractions. So it has the weaker London dispersion forces because it has the smallest amount of electrons. So then another question, which one should condense at the lowest pressure? Blah. Okay, so unpack that. First off, what does it mean to condense?
Gas to liquid?
Gas
Or is that
to-
liquid to solid?
No, condense is gas to liquid, right? That's the condensation on your bathroom mirror when you're taking a shower. Okay, so going from a gas to a liquid, and at the lowest pressure means that lowest pressure here means that you don't have to push it to make it happen, right? It just happens on its own. So who is going?
That has stronger.
Yes.
Right.
Stronger forces.
So the one on the right.
The one on the right.
Yes. Okay. So see what I mean about having to, you have to break apart what it is that they're actually, like, what is the thing they're talking about, right? So boiling point, what does that mean? Condense, what does that mean? And then say, okay, so if they want the lowest, what does that mean? Do I need strong or weak? So you have to break down the question just a little bit first before you go into it.
All right.
Okay. Okay. So that's like the main thing. That's like the big topic here. Properties of solids and the properties of liquids. These next couple of slides, it's kind of like duh. So phase changes and intermolecular forces. Okay. So again, you have to remember when you are changing phases, you're not breaking bonds, you're breaking forces.
Yes.
Okay. You are not breaking bonds, you are breaking forces. So we already talked somewhat about vapor pressure, and boiling point is related to how strong those forces are. So weak forces means you have a low boiling point because it is easy to boil. If you have weak forces, it's easy to pull them apart into gases. And if it's easy to turn it into a gas, that means you also have a high vapor pressure.
Mm-hmm.
Okay. Now, if we're talking about solids, there's also this whole thing about intermolecular forces at play. So melting points are going to go along with how strong you are. You can also have intermolecular forces influence things like viscosity and adhesion and cohesion, all that sort of stuff. Viscosity is like the difference between honey and syrup. Which one of those is more viscous?
Honey.
Honey, right? So you can think about, so you can imagine if you were to like super zoom in on the molecules inside the honey versus the molecules inside the syrup, how do the ones in the honey sort of compare, would you imagine?
They're closer together?
Yes. Yeah. So viscosity does tend to go towards strength of attraction. If you have stronger attractions, you are going to be more viscous because you're like almost to the point of being a solid.
Yeah.
Okay. Okay, so comparing ionic and molecular stuff. We've done this before. Ionic compounds, all right? So these are salts, basically. Low vapor pressures, because have you ever even heard of a gas salt?
No.
No, not a thing. Very high melting points, right? Because it takes a lot of energy to break all those Coulombic attractions between the ions. Very high boiling points, because again, ain't nobody ever heard of a gas salt. And they are brittle, all right? Because they make those pretty little crystal lattices. They are very easy to shatter. And when you do, when you apply any sort of pressure at all to that crystal, you all of a sudden go from super attraction with everything to, if you shift it a little bit, now you've shifted all the charges next to each other, and now they're all of a sudden repel. So they don't like that.
Miss Baskin?
Yes.
I know we talked about this like before, but what's the thing about graphite and the fact that it writes and the other lattices?
Yes, we are going to get into that in this unit.
Okay, cool.
Network covalent solids is the word you are looking for.
That was that was the one where it was like how graphite and diamonds are both just carbon, but it's just like which one is more compressed.
Yep.
Okay.
Okay. Ionic compounds conduct electricity basically when the charges can move, so when they are either dissolved or as liquids. Okay, molecular compounds. So basically you can just look at each one of these things and say it is the opposite of. So molecular compounds, they have weak forces, which means they have fairly low melting and boiling points. They have higher vapor pressures. They don't conduct electricity because they don't have any charges. And then you can actually have incredibly large molecular solids, like really big things, carbohydrates, lipids, big fatty molecules. Hell, your DNA, like that's a molecular solid. It's a big old thing. Now, you're worried about graphite. Covalent networks. So this is when you have a three-dimensional repeating pattern of a compound, right? It is not a distinct little molecule, right? Water is a molecule. Carbon dioxide is a molecule. Diamond is not a molecule. It is a repeating pattern of a covalent solid. Graphite is not a molecule. It is a repeating pattern of a covalent solid. So these are what we refer to as covalent networks. They only happen with nonmetals, and there's not even that many examples of them. So we have diamond and graphite, which are both forms of carbon, and the difference between those, diamond is carbon with sp3 hybridization, making tetrahedrals. And graphite is carbon with sp2 hybridization, making flat planes. That's the difference between them, which is kind of weird, but so be it. Then you can also have things like silicon dioxide, which is a common network solid that they talk about. That is quartz, glass. That's the kinds of things that silicon dioxide makes. It has a very similar arrangement to the diamond, so you get tetrahedral shaping there. But so you can have that. These are not the same as little tiny compounds because they are very, very large structures. They have a much more pronounced set of properties. So they have very high melting points, and their three-dimensional structures are very rigid. And the things like graphite, because they make just big sheets, they can be considered to be very soft because it's like sheets of paper floating past each other. So literally, if you remember that your network solids are diamond, graphite, and silicon dioxide, like that's the thing to remember. Those are the ones that you end up having. They don't tend to ask about other random ones beyond that. So, right, so here's some of your examples of these things. So you can see that these are just repeating patterns going on and on and on and on. Not distinct molecules, but you get tetrahedral shaping in most network covalent solids, which is why they are so strong. So that is why diamond is literally the strongest compound, the strongest substance that is known, is because of its insane bonding strength here in the network covalent solids. These don't have intermolecular forces. These are nothing but bonds. That's the difference. So this is just bond on bond on bond, like more bonds, just repeating units of bonds.
So, Ms. Baskin?
Yes.
So like this is if you were to like write, would you say like it was like a whole bunch of C2s connected to each other, or just like C and then some other subscript, like for those, like, because if they're both carbon, right, how do you tell, like if they give you a formula, how would you tell the difference? Because if it's like diamond and both graphite are both carbon, how do you tell?
So they would, you know how we have the little subscript of S, L, or G?
Mm-hmm.
So they would have the little subscript S and then a comma, and they would tell you diamond or graphite.
Okay.
As the solid form. They have to, because otherwise you wouldn't know, because they do have the exact same chemical formula. Yeah. And there actually are things beyond diamond and graphite. Carbon makes at least 4 known network structures, but carbon or diamond and graphite are the most common. So I think it's more likely that they might say give you a picture of this thing here on the right and identify this as a carbon, but not say that this is the word graphite, and then ask you some questions about it, right? Or give you one of these sorts of structures and identify this as, like that's more likely. They're never ever going to have you draw it, but there's a possibility that they might ask you questions. In this instance, I don't think, since it's a smaller test, that they would ask anything about the silicon dioxide and the silicon carbide or some of the other network solids, because they're just not as common. They could tie in asking other questions about carbon or about the structure of carbon, about the bonds of carbon here that they wouldn't be able to do with these. So I still think this is a pretty small chance of being on the test, but it's always possible. Okay, let's do a couple of quick practice problems and then we'll call that a day. So a white solid has these properties. It's soluble in water. So already, if it's soluble in water, does that seem to indicate ionic or covalent?
Ionic.
Ionic.
Okay.
That's salt.
All right. The solid is soluble in chloroform. So looking at this, chloroform, is chloroform polar or non-polar?
Polar.
Ms. Baskin?
Yes, Carl, it was polar. Yeah, Sean.
It's polar, but when you do, just for my refresh, you put in the center when you do if I were to do like the Lewis dot, you put the most electronegative or the least electronegative thing in the middle?
The least, the farthest from fluorine.
So I would put carbon in the middle.
Yep.
Okay.
Yeah. All right, the pure solid does not conduct electricity, but the aqueous solution of the solid conducts electricity. So all of this is leading you to believe that this solid is a what? Ionic or covalent?
You said the solid?
Mm-hmm. The white solid does all these things. It dissolves in water, but it also dissolves in this polar thing, chloroform. The solid doesn't conduct electricity, but the solution of it does. Ionic or covalent?
I'm sorry, Can you say that one more time, please? There's a lot going on in this room. I apologize. Can you say that one more time?
Okay. So, based on this information, would this thing be classified as ionic or covalent?
Ionic.
Well, it would be ionic. Well, when it dissolves, yeah.
So,
bipolar covalent.
Look at number 5. When the solid is melted, the resulting liquid does not conduct electricity.
Huh?
An ionic solid is going to conduct electricity. All right, an ionic solid, when it melts, is going to conduct electricity, but a polar covalent will not.
Okay, so, but even though because when it's dissolved in water, it conducts electricity, that's something that polar covalent things do.
Yes. So a polar covalent thing is going to be soluble in water because water is also polar. A polar covalent will be soluble in chloroform because it's also polar. A polar covalent compound will not conduct electricity as a solid, but it will most likely as when it's dissolved in a solution, but its liquid is not. So I don't think they'd ever get that. They typically only ask about ionic or covalent for that. Anyway. Okay, so in which of the following are chemical bonds broken? So looking at that, are any bonds broken in that process?
No.
No, only forces. You're going from liquid to a gas.
Yes.
Yes, because in either of these things, carbon graphite and carbon diamond, that has no forces. It only has bonds, right? Graphite and diamond only have bonds. So to go from one of those forms to another, you are breaking and rearranging bonds. Going again from a solid to a liquid, any change in state is just breaking forces. All right, those are just breaking forces. All right, strong electrolyte. Do you remember what electrolyte means?
Yes. It means it's when a salt dissolves in water or it dissolves in like a liquid, right?
All right.
And it's very polar.
Yes, so strong electrolyte means it dissolves easily. You get lots and lots of ions. So is that going to give you any ions or do any dissolving?
No.
That one?
No.
That one?
No. Those are all non-polar, right?
Right. So the KF will, because it's a ionic thing.
Highly electronegative.
Yes, you see your fluorines. So that's it for today.